Hi, today we will learn diffraction of light, a topic in wave optics. We will say how shadow region is formed. Here we have a small aperture, a small hole, which has order of wavelength of light, and we know that light travels along a straight line. This is your rectilinear propagation of light. According to rectilinear propagation of light, light travels along a straight line. But we will see that when this light passes through this small aperture, it bends at the edges. Here it has bent through some angle. And we should have a shadow region up to this length, but we find that we have dark shadow region up to this length, which is called umbra region, and a partial dark region up to this length, which is called penumbra region. So light has entered into shadow region, geometrical shadow region. Now you can take another case also, in which you have an obstacle instead of your one opening, small opening. You have here one obstacle. So when light is hindered by this obstacle, then as per rectilinear propagation of light should travel along a straight path. But it fails the principle of rectilinear propagation of light. It bends at the edges and light enters in shadow region. So you have two parts of shadow region, one dark part and a part where light has entered. The dark part is called umbra region and the partially dark part is called penumbra region. Now what is the cause? So all this can be explained by the Huygens principle. According to Huygens principle, a wave front is the position of new secondary source of light. Here you have a wavefront created and at this point, and you will find that at each point of this wavefront you have a secondary source, and this secondary source is emanating secondary wavelets in all directions, and this can explain, Huygens principle can explain the bending of ray of light at edges. And this bending of ray of light at edges is called diffraction of light. So when light passes through a small aperture, small hole, or hindered through a small obstacle, then it bends at the edges, and this bending of light and entering of light in shadow region, geometrical shadow region, is called diffraction of light. Now, diffraction of light can be observed just behind the door. You can see the shadow region with alternate dark and less dark region of different widths. Behind the door, you can observe. And there is one diffraction which can be seen during morning sightseeing near mountains. Here you have sun hiding behind. You cannot see light in front of it. Sun is behind the mountains and light rays are coming along this direction. Now due to diffraction, the light is bent through this angle, and some portion of mountain you can see become illuminous. So this is due to diffraction of light. So these are two examples of diffraction of light. One is the shadow pattern behind any door, and other is the mountain range, the top cliff of mountain range become illuminated. It is illuminated even though the sun is behind the mountain in the very morning. So this is diffraction of light. Now there are two kind of diffractions. When you have here source is very far away, obviously it will be at infinite distance, and screen also is at infinite distance from observer. You are observing this phenomenon from very far. So if the screen and the source of light is very far at infinite distance, such diffraction of light is called Fraunhofer diffraction. And this helps you in mathematical analysis. So we will be using this Fraunhofer diffraction. Now second diffraction is called Fresnel diffraction, in which the distance between source and observer, source and screen is finite. It is not infinite. So these are two diffractions. Now your Fresnel developed a very meticulous integral mathematics of integral mathematics to find the diffraction patterns and intensity of diffracted light. But here we will be doing with an easy process using your just logical consistence and using hygiene principle, using interference, all these things. We will be finding the intensity of light without going through those long integral calculus of Fresnel. We will do with a very simple process. Now you have other observations of diffraction also. Your eyesight is having some limit of resolution. You cannot resolve all the objects very far from you. Optical instruments like microscope, telescope also have some limit of resolution. Now what is this resolution? When two very closely placed, very far placed objects, very close to each other, when viewed from yourself, then they cannot be separately recognized, because the image formed of the two objects have their maxima coinciding. And this is only due to diffraction of light, that their maxima, they coincide. And so why we cannot see two separately placed objects very far from us separately. They will become a single entity when we view. And here we are unable to resolve the two objects separately. And here how diffraction limits our resolution of eye lens in microscope and telescope. Now at one more place you can see diffraction effects. You can see several colorful light coming from your CD disc. That is actually due to diffraction of light. So now we are going to use Fraunhofer diffraction, because in mathematical analysis it is very helpful. In Fraunhofer diffraction, the source and the screen is at infinite distance. And to obtain this in laboratory, we take help of two lenses, convex lenses, and we put the source at the focus of it, so that light ray become parallel as if they are coming from infinity. And then after diffraction also we place a lens in the path of ray of light, so that they can be focused on a single point and can be observed. So these are the things. Now what is the path difference? So here optical paths are equal up to this length. When you draw a perpendicular, these lengths are equal. So there is a path difference of this length. When you subtract this length from this one, you will get a path difference. So path difference, for finding path difference, And for finding your intensity pattern, intensity changes, let me take a point somewhere here. I have taken a point, and this is your central most point C. Here the rays will come in phase. Therefore, you have a bright maxima at the central most point. So you took 2 points, one central point and a point P above to it. Now this point P, it is at an angle theta. You can see it is an angle theta. So it is making angle theta in between the two rays. So therefore, the same angle theta will be made in between the perpendiculars of these two rays also. So you have a perpendicular here and you have another perpendicular here. So the angle will be same in the two cases. This will be your theta. Now from here you can find path difference. You know that sine theta is equal to perpendicular, and this perpendicular is your path difference. Del x, perpendicular upon base, and base is your, this aperture has thickness A. So therefore path difference comes equal to A sine theta, and for small angle sine theta becomes only theta. So this your path difference is A theta. Path difference is A theta. Okay. Now let us find out the position of maxima and minima. At which path difference there will be maxima and at which path difference there will be minima. So if you for that we will be dividing this aperture into two parts or even number of parts. 2 parts or 4 parts or 6 parts. But for simplicity I have divided it into only 2 parts. So this path is, if this path is taken as lambda, let the path difference is lambda. Then half of the path difference, and it is, we have obtained it is equal to 2 theta. We have just obtained, not 2 theta, sorry, it is A theta. Okay, it is A theta. And therefore you find by the similarity of the two triangles, this triangle and this triangle, if this path difference is your A theta, then this path difference will be equal to A theta by 2. Because here it becomes half, and we know that in similar triangle ratio of the sides must be equal. So ratio of this side to this side, then you will find that this side also become half of this path difference. Here you have A theta upon 2. So let us assume, now let us consider the two cases. Firstly, when let us assume that this path difference is lambda only, then if this path difference is lambda, this path difference will become lambda by 2. So for every particle m1 in this your first part, every particle m1 in first part, there will be a particle m2 in second part, so that path difference between the two will become lambda by 2. Here the path difference of the waves coming out from these 2 points have path difference lambda by 2. So if path difference is lambda by 2, then you will find phase difference. You know that for lambda path difference, phase difference is pi. Therefore, for lambda by 2 path difference, for lambda path difference, phase difference is 2 pi because a complete cycle. So pi plus pi, 2 pi. So for a path difference of lambda by 2, phase difference is your only pi. Pi means 2 waves are coming. one is going downward, one is coming upward, they are opposite in phase, so they will cancel each other. So there will be minima for each such interference, for each such superposition of two rays coming from every M1 and to their corresponding M2. There will be a minima. So they will cancel each other, there will be minima. So at the path difference and lambda, we will have minima in diffraction. And if you could recall, in interference at these path differences and lambda we had a maxima, whereas in diffraction we have a minima at n lambda. Now let us consider another case. We have divided this aperture into three equal parts. You have divided, here you have three lights. Let me take the lights. One from here, another from here. Okay, let me change the color. One from here, another from here. Now you have three parts, you can see. So path difference for this part is this much, so path difference will be reduced. Path difference will be reduced. And you will find that if path difference for the longest part is 3/2 lambda, so it will be obviously 1/2 lambda, 2 lambda by 2 and 3 lambda by 2. Therefore for two parts you have part difference only lambda for two parts. So for all points in first part, that is M1, there will be a corresponding part M2 in second part, for which path difference becomes equal to lambda. Okay, this is your lambda. This is your lambda. Then if you divide this lambda in the two parts, then you will find that path difference becomes lambda by 2. So for every part, you will find that for every part in every point in first part M1, there will be a point M2 in second part, for which you will find that path difference becomes lambda by 2, because total length is your lambda. For the two parts, you have total length lambda, and for the half you will have, for M1 and M2 in the two parts, you will have lambda by 2. Okay. So the path difference for the two particles is lambda by 2, and so you will find that the phase difference becomes equal to pi. By the same formula, lambda tends to 2 pi. And then lambda by 2 tends to pi only. Okay. So phase difference is pi. One wave is coming in downward direction. Another wave is in a phase in upward direction. They will cancel each other. Now the resultant intensity, the two parts have cancelled each other. The two parts, the light from two parts, the wave from two parts have cancelled each other, and you have left with third part. So you will find that the resultant intensity and resultant, I should say, amplitude will be, resultant better I should say, amplitude of vibration or intensity, okay, intensity of vibration will be only equal to one third of the remaining. So when you take path difference by this formula, where is the formula? N plus half lambda. When you take path difference 1 plus 1 by 2 lambda, that is 3 by 2 lambda, then you will have intensity remained 1 by third of 1 by third of the intensity. Now, when you take path difference larger, you place instead of 1, you put the value of n as 2. So it will become 5 by 2 lambda. So when path difference has increased, suppose here you have another wave. This was the first wave, and now path difference has increased. So you have taken a wave along this way, and here you can see that path difference has increased. So the path difference has increased, and you will find a pattern at this very point, another point. Instead of P, you will find for larger path difference, you will find a pattern on Q, another point. Then you will find that you have path difference 5 by 2 lambda, and thus when you have 5, you have 2 plus half lambda, and when you divide whole of the slit into 5 equal parts in this very case, then 4 equal parts will be cancelled. The two corresponding part will cancel the intensity of light for themselves, and two other parts, light coming from two other parts, will cancel each other. Now you are left with only one part out of 5. So you can assume that the intensity of light should also decrease proportionally 1/5 of the intensity of light. Or if it is amplitude, intensity will be decreased by more, square of amplitude. So intensity reduces. Simply you can say intensity will reduce if amplitude reduces 1 by 5th. Intensity will be reduced by square of this. So intensity is reduced by a large magnitude, large amount. Maxima, for second maxima, for third maxima, you will find the intensity of light goes down. It is in contrast of the case of interference, where you have the fringe width of equal size and have equal intensity. Here you have intensity go down from central maxima. So you will find here we have a diagram. When light comes, the central maxima will have highest intensity. This is your intensity axis. So intensity is highest for central maxima. And then intensity goes down along the two sides. Here you can see intensity is quite small, this much small. And not only this, your fringe width also reduces to half from central maxima. This is half of it, this is further half of it. So two things happen in diffraction that is different from your interference. In diffraction, intensity of light, intensity of fringe reduces from central maxima to both the directions. And also the fringe width, size of fringe width reduces. Now when you have double slit interference pattern, what happens? Each slit produces one diffraction pattern, because you have just learned that one slit produces a diffraction pattern. So when you have two slits, each slit will produce diffraction pattern, and then these diffraction pattern superimpose over each other to have phenomenon of interference. So you get this kind of phenomenon. You have just learned that diffraction pattern is of this shape, intensity is highest, and now interference pattern also is formed. You can see in central maxima. Here the two diffracted light beams are interfered also to give alternate maxima and minima. Now the number of these fringe widths. in central maxima will be equal to, suppose you have two slates and the distance between the two slate is D, and this slit is of width A, then the number of fringe in central maxima will be equal to D upon A. So if you reduce the width of one slit, one hole, then the number of fringes will be increased. And when you increase the distance between the two holes, then also number of fringes in this central maxima, in this diffraction pattern, will be increased. Now, what is the difference between interference and diffraction? So you will find that interference is produced by few sources of waves, few sources. That just I have taken two sources of light, 2 or 3 or 4. These small number of sources of light do interference pattern. But when you have many sources, large number of sources of light, then they will produce diffraction pattern. Now, maxima in case of interference is produced at n lambda, where maxima in case of diffraction is produced at n plus half lambda. And just contrast of it, the minima in interference pattern is produced at a path difference of n plus half lambda, whereas the thing is inverted in this very case in diffraction. Here the minima is obtained at n lambda. Now, one last difference between the two, that the fringe weights are of equal size and they have same intensity in the case of interference of light, whereas in case of diffraction, fringe weights are of different sizes, and also the intensity of light varies from one fringe to another fringe. Okay, thank you.